Today we're diving into I-JEPA, a joint embedding predictive architecture. I'm going to plan on making a video about V-JEPA, the video version of it, so this will be a foundation for that other video. We'll explore how it avoids a notorious problem in self-supervised learning called representation collapse. And we're also going to talk about how I-JEPA is actually different than the earlier methods like MoCo, SimClear, Dino, and VicReg. We're also going to talk about how I-JEPA is actually the starting foundation of the ultimate goal here, which is to build a world model. So what's the problem with collapse? So at its core, collapse is when a network is actually learns to map all of the inputs to the same representation. So as opposed to taking advantage of the full embedding space right here and perhaps map a dog here, map a cat here, map a horse here, it's actually going to collapse all of these to the same point. So all of these different images, whether it's a cat or a dog or a traffic light, they're going to get encoded into an identical embedding vector. So this one shows a complete collapse. This one shows just a collapse along the dimension, where the embedding vectors, it only spans a lower dimensional space. If you contrast that with supervised learning where you do have labels, the labels are going to force the separation. So if one image is labeled as a cat, the other image is labeled as a chicken, well, the optimizer is actually going to arrange their embeddings in such a way that they're going to be in different space, in the complete representation space. So collapse here doesn't even exist because the labels are the ones that are actually imposing the structure. When it is self-supervised learning, the only training signal here, since you don't have any labels, is an internal consistency. So there is no labels. You generate two different views and you actually pre-process the views. In this case, you change the color. In this case, we crop out a zoomed in version of the dog and you pass those to the same encoder, and you're trying to put them in the same space. But if the only requirement is that augmentation of the same sample should match, then the network is going to learn the easiest solution, since it's based on the loss function, and it's going to simply map everything to the same vector, to the same point in the representation space. And so a normal learning is going to have this type of trajectory, but when there's the collapse, the loss is going to be straight down to zero. It's going to learn a trivial solution, but it's actually not learning anything. So that is why collapse is such a pervasive threat in self-supervised learning. So whenever the learning objective is self-referential, there's no labels, the system is going to try to match itself. So you can minimize the loss without doing any real learning. So there's families of self-supervised methods which actually try to artificially put some structure in the embedding space to avoid the collapse. So methods like MoCo and SimClear, they introduce the idea of negatives. So these are embeddings from other images that serves as a distractor. So the loss is going to say, pull together the images of two augmented views of the same image and push apart the embeddings from the other images in the batch. So these are the negatives. And as you pull things apart, the other things are going to group together. And that's how you form these clusters within the representation space. So this is going to solve the collapse. And so the optimizer is going to be forced to carve out distinct regions in the representation space. However, they're doing this by artificially shaping the representation distribution. So because every embedding is pushed away from every other, the method is actually implicitly enforcing a kind of a uniform cluster prior. Embeddings are actually encouraged to spread evenly across the hypersphere, which is okay. However, it doesn't align with real world data distributions, which is mostly long tail. So some categories are going to be, you can have 10,000 cats and you can have other categories like hedgehogs, and you only have 50 examples of those. But if your objective forces clusters to occupy roughly the same space, regardless of the frequency of it, then you're going to have distortions. So frequency categories are going to get compressed, like here. So the large cat cluster, let's say this is the cat cluster, is going to get artificially squeezed to make room for others. And rarer categories are actually going to inflate. And so the issue is that your representation space, it no longer reflects the true distribution of the world. It looks nice, but it's going to be misleading. Another set of self-supervised learning methods called entropy regularization methods like Dino, Bring Your Own Latents, and VicReg, instead of relying on negatives, these methods, they actually stabilize the training using teacher-student architecture. And so the teacher is not going to be updated by gradients. Here the SG stands for stop the gradient. So it's not going to actually receive gradients. It's going to learn implicitly through a exponential moving average of the student's parameter. So this means that the teacher is a low-pass filter of the weights of the students. So as the student learns fast, the teacher is going to learn the same thing but slowly. It's going to average over many past student states rather than immediately copying what it just learned. Because that's really important, because if the student decides to collapse, which means that all embeddings become like a constant vector. That means because the teacher has the memory of what the student learned before, is going to realize that now the student is trying to cheat. And it's not going to allow that. It's going to penalize the cheating that the student is trying to do, or aka the collapse. So basically the student's constant predictions, they're going to fail to match the richness that the teacher is going to have. And so you're going to have a large error signal. So the gradients are going to push away the student from the collapse solution back towards what the teacher is used to. And so EMA is a form of collapse prevention, since the teacher remembers the diverse past and is going to penalize trivial shortcuts. But even with EMA, collapse could still happen, so these methods add entropy regularization. So for instance, Dino applies a centering step followed by a softmax sharpening trick on the outputs of the teacher, and the centering, it's going to flatten out the distribution while the softmax is going to sharpen the steps, while the softmax is going to sharpen the distribution. So instead of having a signal that's like this, we're going to center it a bit, and then we're going to sharpen it. So there's a bit more richness going on, and you want the teacher distribution to have high entropy so that the predictions are spread out across different prototypes. However, where's the weakness here is that the entropy maximization is still a form of distribution shaping hack. So we're still trying to artificially tell to balance the prediction across the prototypes so that things are not in balance. You want things to be balanced out. And that's a way, the centering and the softmax is a way to balance out, to spread out the features so that there's richness in there. So the issue here is that, yet again, the clusters don't reflect true category frequencies. So just to wrap up, we spoke about certain self-supervised methods like MoCo, SimClear, and Dino. They rely on a way to shape the distribution artificially through contrastive objectives with negatives, or you're trying to maximize the entropy, or you're trying to use centering or clustering, and being forced to spread out the features evenly across the space. And that's useful to prevent the collapse, so they did a good job there. But the catch is that distributing those features artificially comes with side effects. And so you're assuming that the frequency of the data in the real world is the same. You have as many frequency of cats as like another really rare animal. It makes the model very sensitive to mini batch composition, and there's other symptoms as well. So the way I-JEPA solves this is it doesn't try to reshape the distribution artificially, but it tries to predict something from something else it already knows. So the objective is purely predictive. So you're trying to mask a part of the embedding, and you're asking whatever the rest of the embeddings that it can see. Based on that, I try to fill in the gaps. So it's trying to predict missing semantic content. So this way, the model is actually going to learn structure from the data itself without trying to force some balance. And there's no built-in assumption that the clusters must be balanced equal size. So the way it works is that you feed the model an image, and a part of the image is going to be masked out. You pass that through the context encoder, and you're going to have a representation of the visible part. And you take different possible parts of the same image. Right here, and right here, you feed those through the target encoder, which are going to be embedded into the representation space right here. And then you're going to have a predictor, which is these, and they're going to try to guess based on the context that I know that I've just encoded, and based on these locations, I'm going to try to predict what goes inside here. And this works at a representation level, not at the pixel level. And just to be clear, we're not going to mask out the input pixels themselves. We're going to mask the output of the target encoder. So we're going to first encode the whole image unmodified, and then we're going to mask out the parts then we're going to mask out the output of the target encoder right here. So all of the predictions are going to be all about semantics, not about the pixels. So we're trying to make it learn in high-level semantic representation. So because of the model is trying to predict in representation space, I-JEPA can focus on the semantic structure rather than the details of the pixels, which can be wasteful. So you're reducing the amount of compute needed. So I-JEPA can actually learn as much, but with fewer iterations. So I want to zoom in a bit on the predictor here, because it's pretty important. So think of the predictor as a puzzle solver. If I have a piece that I know what it is, and I'm trying to fit a piece at a certain location, so this is one location, this is another location, this is yet another location, then what I'm going to expect to be at this location has to make sense. So this, if this is a tree, let's just say, at this location right here, it can be a sun, it can be the sky, it can be a mountain, something that's higher than a tree. I'm not going to expect, for example, a person in the sky or like a house in the sky. So the predictor must capture this uncertainty instead of collapsing to something that's rigid. So we're trying to predict here conditioning on the position of the mask token. So the predictor is going to learn that I'm filling a patch at this location, and depending on the context right here, there might be several valid possibilities. And it's really important to note here because that's the starting point of a world model. It tells us what is possible and what is not possible. So this work is going to be extended to videos as well, which is what I-JEPA is about. So in I-JEPA, TLDR, given something that happened in the past, I can predict possible outcomes for the future. So this model will tell what is possible and what is not possible, which is a key characteristic of a world model. So the researchers wanted to test the predictor. So does the predictor actually encode this positional uncertainty? Is it producing predictions that depend on the location of the masks and the context, or is it just collapsing to oversimplified guesses? And the results show that the predictor of I-JEPA is actually learning rich, contextual, location-aware semantics. Not just trivial completions. If I have the context and I'm trying to fill this gap, well, you're going to have something that looks reasonable, like the snout of a dog. Or if it's here, you're going to have a snout plus the leash that goes around the neck of the dog. So the model learned that it's possible to have a leash there. Same thing right here, given this context and conditioning on this location, what do I expect? I expect to see the face of the dog, which is correct. At this point, for example, I don't expect to see the face of the dog, and it drew the rest of the dog. So it does learn what is possible and what is not possible. So to review the architecture of the I-JEPA, the same input is fed to the student encoder and the teacher encoder. Mask will be generated after that. The location of the mask are going to be here. The objective of this architecture is that we're going to try to predict certain parts of the image given the context, which is right here. The location of the image we're trying to predict is going to come from the mask. And so the predictor, like we said, is a puzzle solver. So given the context and where we're trying to predict, we're going to minimize that. And that's how the system is going to learn. We're stopping the gradient to avoid collapse, and we're updating the teacher through exponential moving average, which acts like a memory of what the student has learned so far, so that if ever the student tries to collapse to a constant vector, it's not going to be able to match the very diverse, rich output of the teacher. And so the loss is going to spike, and the student will be pushed back towards outputting something that has diversity. So it's a way to prevent the student from cheating, which is what collapse is.